Hey guys, I welcome you all. I hope you guys are doing good. I am Aditya from RV College of Engineering. Today I am going to give you a gist about nanomaterials for solid oxide fuel cells. I hope you enjoy the video. Now we shall discuss about what are solid oxide fuel cells. Solid oxide fuel cells or SOFC, an electrochemical conversion device that produces electricity directly from oxidizing a fuel. Or these are basically devices which operate at high temperatures. These devices also convert chemical energy to electrical energy. Fuel cells are characterized by the electrolytic material. Solid oxide fuel cells are a class of fuel cells characterized by the use of solid oxide materials as the electrolyte. SOFCs use a solid oxide electrolyte to conduct negative oxygen ions from cathode to anode. Electrochemical oxidation of hydrogen, carbon monoxide and other organic intermediates by oxygen ions thus occur on anode side. SOFC is an important fuel cell and it consists of two porous components, anode and a cathode. It is separated by a highly dense component electrolyte such as YSZ and GDC. Now let us see why nanomaterials for solid oxide fuel cells. Fuel cells have a great advantage over system because of the high electric efficiency and fuel flexibility. SOFCs have many advantages for a wide range of applications because of their electric efficiency, potential to use natural gases, biogases and CH4 as fuel and perform high. Many researchers have mentioned fuel cells are very important due to the lack of noise and pollution. Although many electrode materials for SOFCs have been developed over these past 3 decades, challenges for cost and limited durability still exist. Therefore, great effort is being made to overcome these challenges by designing new materials at nanoscale level, which may lead to improved SOFC performance in different applications at reduced temperature. Nanotechnology is utilized well in the development and improvement of the performance in solid oxide fuel cells SOFCs. The high operating temperature of SOFCs, that is 700 to 900 degrees Celsius, has resulted in reduce of overall performance and durability. Therefore, the operating temperature has been reduced to an intermediate temperature of approximate 400 to 700 degrees, which improved performance, sustainability, commercialized SOFC power sources. Now let us see the working of solid oxide fuel cells. SOFC has two reactions, one at the anode and the other at the cathode. At anode end, natural gases which is CH4, methane gives H2 plus CO. Fuel passes over the anode. At cathode, abundant air O2 is present. Air passes over the cathode. As long as fuel, air and heat, the process continues producing clean, renewable and affordable energy. And then we can see oxygen ions react with the fuel in fuel cell. At anode, we can see H2 gives H2O and CO gives CO2. We have electrolyte between the anode and the cathode, where cathode has O2, which is the oxygen molecules. Anode and cathode are made from special inks that coat the electrolyte and require no precious metal, corrosive acids or molten materials. After all these reactions take place, we can see reaction proceeds to produce electricity. Now let us see why solid oxide fuel cells in energy conservation. The consideration of fossil fuels, oil, coal, natural gases as well as long-term energy resources is becoming difficult to justify. Especially carbon dioxide, nitrogen oxide and greenhouse emission are considered to be major contribution to global warming. It is very important to consider the usage of alternative sources, renewable and sustainable ones, and it can be able to stand with the human need, and the most obvious way for small sustainable farms can help in reducing the nation's dependence on fossil fuels. The key benefits that highlight the improvement role of SOFCs are reduction of CO2 emission from 90% to 35%. Reduction of fossil fuel usage from less than 80 to 90%. Reduction of air pollution by 90%. Now let us see the operational approaches of SOFCs. Typically, the functional operation of SOFCs is mainly depending on the transformation process by means of H plus and O minus in the electrochemical reaction. The main reaction of an SOFC rely on anode feeding by H2 and the cathode feeding by O2, and the whole transformation process as clearly presented in the following equations. H2 gives 2H plus 2 electrons. Half O2 plus 2 electrons gives O2 minus. H2 plus half O2 gives H2O. From anode, H2 plus O2 minus gives H2O plus 2 electrons. CO plus O2 gives CO2 plus 2 electrons. From cathode, half O2 plus 2 electrons gives O2 minus. Now let us see a few important points about fuel cell technology. Principles of operation and features, advantages and limitations, challenges and development issues, applications. Advantages: highly efficient, simplicity, low emission, flexibility. Limitations: relatively high cost. Applications: transportation, structure, military use, remote villages, aircraft and airspace. Now let us see in detail the anode and cathode reaction in a solid oxide fuel cell. The importance of developing anode material as the main part of the fuel cell contains because the percentage of material being used in the part nearly above 95% of the used material in the cell is in anode supported cell. In order to maintain a high performance of anode material, it should be highly conductive, chemically compatible, thermally sustainable, highly porous structure and fine particle size with an organized structure. However, in the meantime, common anode materials are traditional particles that have been used for a long time despite existing poor performances. In the given below picture, we can observe the materials that can be used as anode in SOFCs. And we can also see the cell reaction of solid oxide fuel cell. Now let us see the electrolyte and intermediate materials. In an SOFC, it may be an anode supported fuel cell or electrolyte supported fuel cell. Both case the role of electrolyte is essential as it must possess high ion conductivity, chemically and mechanically compatible with the other components of the cell. Electrolyte plays a very important role in the SOFC. Now let us discuss about the electrolyte and intermediate materials. In an SOFC, it may be an anode supported fuel cell or electrolyte supported fuel cell. Both cases, the role of electrolyte is essential as it must possess high ionic conductivity, chemically and mechanically compatible with the other components of the cell. Electrolyte plays a very important role in the SOFC devices. The most commonly used material is GDC. Therefore, the interconnection must be a dense material like the electrolyte, which is a good electroconductor and oxide ion insulator, chemically sustainable in both oxidizing and reducing atmospheres. Next is the cathode material. The second major component in fuel cell is the cathode part, which has a contact layer with the electrolyte and exposed to air. The importance of this electrode part can be explained by the functional working of the cell operation through the cathode and oxygen reaction. Lanthanum manganite composition doped with rare earth elements such as COCESR showed good performances as cathode in solid oxide fuel cells. For any material used in SOFCs as cathode, firstly, it should be highly electronic conductor. Secondly, it should be chemically compatible and thermally sustainable, matching with other components of the fuel cell unit. Thirdly, the microstructure should be in high percentage of porosity for oxidation reaction at cathode electrolyte interference. Fourthly, it should offer highly catalytic activity for O- during reduction reaction. And finally, it should be cost efficient to manufacture. Next, we can see the materials used in anode, cathode and electrolyte. And also a fuel cell of SOFC. Next, we have the challenges and limitations of SOFC. The major challenges and limitations in SOFC devices are the proper selection of material based on its properties can be clearly identified through the following. The hazard of poisoning due to coke and sulfur deposition, surface diffusion, distortion of charge transformation in anode, restraint of O2 migration that is responsible for electrochemical reaction occurring in solid electrolyte, total mismatching of coefficients of thermal expansion for the whole fuel cell, chemically unstable and incompatible in the oxidation and reduction environments. Now let us see how we can overcome these challenges. Briefly, these challenges can be overcome by extending startup of fuel cell burning, hence the startup time for FOFC operation will be prolonged. Sealing problems can be solved by relative CTE or adjoining materials that does not react with the joining parts. Included thermal stress at electrolyte electrode interference, which causes interdiffusion between cell components, can be controlled by keeping it under wraps during FOFC operation. Now let us discuss the advantages of solid oxide fuel cells. Nanoscale materials have found their vital role in scientific communities. The advance of SOFCs in lowering its operating temperature has opened up a new prospect for applications of both micro and nanomaterials. For instance, the NiYSZ-PT has been investigated at 600 degrees for 10 hours with dry H2 and air. The obtained power density was 23.3 milliwatt per centimeter cube. On the other hand, by using NiYSZ-PT, power output of 150 milliwatt per centimeter cube at 500 degrees Celsius was observed at humidified H2:N2, which is at the ratio of 1:4. I would like to conclude my video with a clipping of solid oxide fuel cells.
As the demand for reliable, clean electricity grows, we're faced with challenges such as an aging grid infrastructure, natural disasters, and rising electricity costs. Bloom's energy servers convert fuel into electricity through an electrochemical process without combustion at the highest efficiency of any power solution available in the world today. Designed for modularity, similar to a building block, any number of our systems can be clustered together in various configurations to form solutions from hundreds of kilowatts to tens of megawatts. Solid oxide fuel cells consist of three parts: an electrolyte, an anode electrode, and a cathode electrode. An electrolyte is what the electrical ions move through in a fuel cell. For a solid oxide fuel cell, the electrolyte is a solid ceramic material. The anode and cathode are made from special inks that coat the electrolyte. Unlike other types of fuel cells, no precious metals, corrosive acids, or molten materials are required. Next, an electrochemical reaction converts fuel and air into electricity without combustion. Operating at high temperature, warmed air enters the cathode side of the fuel cell. Meanwhile, steam mixes with fuel, entering the anode side to produce reformed fuel. As the reformed fuel crosses the anode, it attracts oxygen ions from the cathode. The oxygen ions combine with the reformed fuel to produce electricity, water, and small amounts of carbon dioxide. The water gets recycled to produce the steam needed to reform the fuel. The process also generates the heat required to keep the fuel cell warm and drive the reforming reaction process. So long as fuel and air are added, the process continues producing clean, reliable, affordable energy.
Thanks for watching the video. At least a bit of information is shared about solid oxide fuel cells, I guess. Please do like, share and subscribe the video and put your comments below in the comment section. Thank you. Namaskara.